In part 2 of this video, the challenges of 802.11n, we'll start by talking about why co-channel interference can be a major problem also at 5 GHz for the microcell architecture. As I mentioned in part 1 of this video, we can expect 6 to 8 40 MHz channels to be available at 5 GHz if DFS channels are used. Let's take as a use case the first floor of a moderate to large sized high school. The floor dimensions are about 100 meters by 100 meters. Given a planned cell radius of 12 meters, we will need about 16 cells to cover the floor. So assuming the availability of 8 40 MHz channels, then every channel is going to be repeated once in a microcell deployment. That can be a cause of significant co-channel interference. The reason is that lower rate transmissions have a range that is several times farther than the highest rate transmissions. In fact, the range of signal that is powerful enough to trigger the CCA, clear channel assessment, mechanism of another AP or client is quite far, easily 5 times as far as the higher rate transmission range that the cell is planned for. So we can see that there can be a significant amount of co-channel interference between APs on the same channel. The chart in this slide is the proof for what we have just shown. It lists the signal range versus error rate. What's important to note is that the reception range at the lower error rates is far greater than at the higher error rates. In fact, RF energy that can be picked up by an AP or a client CCA mechanism travels even further. So even though the microcells in our example are planned according to the moderate to high error rates, the reality is that the RF energy propagates far beyond the borders of the cells and can cause interference problems. Let's isolate one channel, channel 44, and take a closer look. Working out the geometry of the school floor, it becomes evident that given the RF propagation distances at 5 GHz, there is a good chance that AP2 and AP11 will hear each other if there is significant open space, such as hallways, between them. Both APs are in the same channel, 44. When AP2 transmits, AP11 hears it, and its CCA mechanism prevents it from transmitting until the AP2 transmission is finished. The client associated with AP11 also cannot transmit because its CCA mechanism picks up the AP2 transmission. So the second red cell is completely inoperative while the first red cell is in use. Even if we assume the cells are somewhat smaller, co-channel interference can still be generated. When the client near AP11 transmits, AP2 hears it and stays off the air. Summing up our discussion of what 802.11n means for microcell deployments, we have seen that the 5 GHz band is viable for microcell 802.11n even with channel bonding. However, there are still not enough channels to avoid co-channel interference in a microcell deployment for medium to large sized installations. And if there are problems on the DFS channels, then as few as 4 40 MHz channels are available, and then the co-channel interference will be even worse and impact even smaller microcell installations. The second key issue that we saw is that in a microcell deployment, the 5 GHz band needs to be deployed for end clients only, and the 2.4 GHz band reserved for legacy devices only. Now let's talk about what the availability of 5 GHz spectrum means for channel blanket deployments. First of all, it means even higher aggregate throughput. As we saw earlier, the channel blanket makes very good use of the 2.4 GHz spectrum and is even able to operate 802.11n HT mode there. However, the lack of channels means that only 2 channel blankets can be activated in 2.4 GHz when 802.11n HT mode is turned on. Adding 5 GHz operation opens up the possibility of adding another 2 channel blankets for a total of 4 working in parallel. Furthermore, legacy devices don't suffer any degradation in service because of the channel blanket's efficient use of bandwidth. the legacy users get good service at 2.4 gigahertz, and there is also the option to provide a dedicated 802.11a channel if desired. And just as there is no co-channel interference problem at 2.4 gigahertz, there is no co-channel interference problem at 5 gigahertz. We can see in this diagram how 802.11n HT operation is supported on both the 2.4 and 5 gigahertz bands. Also, legacy users are supported on both the 2.4 and 5 gigahertz bands as well. Switching back to our discussion of microcell and 802.11n, we need to talk about cell planning. Cell planning becomes even more problematic in an installation which has to deal with both 5 gigahertz and 2.4 gigahertz operation. MIMO also adds to the complexity, and also the high rates versus co-channel interference introduces another element. The 5 gigahertz and 2.4 gigahertz bands have different RF propagation characteristics, so the cell sizes are different. Optimal AP placement for 2.4 gigahertz is not the same as in 5 gigahertz. The different propagation characteristics of 2.4 and 5 gigahertz are obvious in this chart, whereas at 5 gigahertz 802.11n has a range of approximately 22 meters, assuming some drywall must be penetrated. At 2.4 gigahertz operation, the range is 37 meters, so the cell size of 802.11n at 5 gigahertz is quite different than at 2.4 gigahertz. This creates challenges for cell planning, both the 2.4 gigahertz and 5 gigahertz bands simultaneously. Because the 2.4 gigahertz band in our use case must be compatible with legacy clients, beacons are being sent at 1 megabits per second, and so the interference range in the 2.4 gigahertz band is quite long. Let's assume for a moment that cell planning focuses on the 2.4 gigahertz band. If the APs are laid out according to the 2.4 gigahertz cell plan, then the AP spacing will be too great for the smaller 5 gigahertz cells. Many 5 gigahertz clients will get reduced rates because they are in areas with very low 5 gigahertz error rates, or even worse, there could be total gaps in 5 gigahertz coverage. On the other hand, if cell planning is done based on the 5 gigahertz band, which makes sense by the way, since we want the best error rates for our 802.11n clients, this is what we'll get at 5 gigahertz. But what is the situation at 2.4 gigahertz? Well, what happens is that the 2.4 gigahertz cells are far too close together for reasonable 2.4 gigahertz operation, raising the co-channel interference to very high levels, even for the higher data rates shown here. So in a microcell deployment plan for 5 gigahertz, the legacy users that need 2.4 gigahertz will get relatively poor service. However, if it's a channel blanket deployment, placing APs according to 5 gigahertz coverage poses no problem at 2.4 gigahertz, as there is no co-channel interference in a channel blanket, even when the cells are closer together than needed. In fact, this situation is actually a bonus for the 2.4 gigahertz users, as most of them will now be in high rate zones. So with a channel blanket architecture, you just go ahead and place your APs according to 5 gigahertz requirements, and the result at 2.4 gigahertz will be excellent as well. There is actually no need for traditional cell planning.